Good evening, everybody, and welcome to the Triangle Area SQL Server User Group's Advanced DBA meeting. So we're going to get started in just a moment. I have to switch stuff over. Look at that. Now I've got camera, but the camera actually shouldn't be up there. The camera should be down about here. I have to switch a few things around. But should be able to get a pretty good meeting. So, okay, that camera's looking good. Look at that. I could actually even be up the top, but really, I'm probably going to be down here the whole time. All right, we are going to talk about database normalization. It is funny, my head going up and down on a black canvas. Yeah, you work with what you got. So we're going to talk about database normalization, an advanced primer on normalization. And if you get nothing else out of tonight's talk, the term is primer, not primer. Primer is what you put on a car. A primer is that walkthrough. So my name is Kevin Fiesel. I run the Triangle Area SQL Server Users Group, which is where you're at right now. I'm a Microsoft Data Platform MVP, and also by day, run a predictive analytics team. I have a blog called Curated SQL, the idea of which is try to find and link to 5 to 10 interesting posts per day on topics all across the data platform space. So that's curatedsql.com. Also, author of a book, got some training, got some other stuff, yada yada. But we're not here for that. And Mike, here's your two Kevins right now. But we no longer have two Kevins. We now have Kevin and a dog. Is this talk right for me? It's a good question. Thanks for asking that question. So have you ever believed, for example, that normalization is not relevant in the business world? Maybe that you normalize until it hurts, denormalize until it works? I hate that phrase, by the way. If ever you want me angry, that's the phrase you use. The main purpose of normalization is really just to minimize disk utilization, remove duplicate data. Or perhaps that database design just doesn't matter. In this modern era, all we have to do is put it in the cloud or add more hardware. That'll fix the problem. Maybe that getting the third normal form is all you need to know about database normalization. Or, well, third normal form is important. If you believe any of these things, this talk is right for you. Because, spoiler, third normal form actually isn't important at all. So what I want to do in this talk is explain some of the basics behind database normalization, but then jump into the deep end. Dive into the two most important normal forms, and we'll briefly cover some of the other interesting normal forms along the way. And finally, I'll talk about some critiques of normalization at the end. So let's do this thing. If you have questions at any point in time, feel free, drop them in chat. Happy to take them at any point. But as a warning, normalization is a part of relational theory. So there will be math, there will be formal logic, just a little bit. I will try my best to keep it as business friendly as possible and minimize that learning curve, but realize that at the end of the day, normalization is a math problem. And also, some of the normal forms that we can talk about are not well understood outside of academic circles. Almost certainly you've never heard of them in the business world. And also, your interpretation of normal forms may not necessarily match what I'm going to describe. The Duke says, crossed fingers, the discussion will cover columnar data and implications. A little bit. We'll talk about that when it comes up. Most of today's source, it comes from C.J. Date's book, Database Design and Relational Theory, specifically the second edition. Is this a deterministic presentation? No. Every time I give it, there is definitely some element of randomness. At least I can say that because this is the first time I've given this talk. And depending on whether it gets accepted again in the future, it may be the only time. We'll see. I call out that this is the second edition of Date's book. There was a first edition, obviously, but What's interesting is that actually going through his book, first edition versus second edition, there are some things that in the second edition he calls out, I no longer believe this. I now believe this. Within relational theory, there is debate. There is subtle shift of what makes sense, what is relevant. And that's even within that realm of formal logic that you'd think would be fairly well settled. But relational theory is still relatively new as far as formal logic exercises go. The first paper's coming out in the 1970s, so it's only been about 50 years. And I don't mean that some tongue-in-cheek, like I'm being sarcastic method. This stuff takes time. So anyhow, grab that latest version of it. I think you'll enjoy it more than the first version. Here's my agenda. We're going to start with the basics, and then we're going to go beyond the basics. So normalization, real short version of it, logical rules and processes to follow. So this works off of a logical data model. And theoretically, what we would do is we would have the ivory tower egghead data architect come up with your logical data model of how things should work, and then hand it off to what we might call database engineers to do the implementation. Similar to how architects create blueprints, engineers implement. And the specific tools and processes that those engineers would use would make it so that it's not necessarily exactly what you see in the blueprint. So in reality, with the implementation of SQL, or of SQL if you prefer, the logical and physical data models you have a limited scope in differences. There are differences. Like, for example, I can choose this particular table, I'm going to use these indexes. Indexes are outside of the world of normalization, outside of the world of database design, strictly speaking, where I mean the logical data model. Their physical data model, how do I make things faster? Choosing whether you want a clustered index as a B-tree index or you want a clustered column store index. Again, that's a physical data model determination that is not necessarily contingent upon what was chosen in the logical model. And so why not both? Basically, what I want to do is I do want to have a theoretical separation between the two, that you may have something which makes sense in a logical model, but may be better served being done differently in a physical model. As a quick example of that, suppose that you have two tables that very quickly or very frequently are joined together. We always join these two together, but they're different things. And in a logical model, we want to separate them. In a physical model, we may actually store the joined contents of both of those tables together physically on disk so that we can retrieve that data quicker. That's a hypothetical because outside of, say, indexed views, you can't really do that in the language, in the relational database management systems that exist today. So instead, we have to blur the two, and basically we have one data model. But I want to pull us a little bit away from that tonight and get into that ivory tower. And to do that, we're going to have a primer on terminology. So we are used to thinking in terms tables, rows, and columns. And in fact, I just used the term tables. And I used the term table on purpose because I was talking SQL or SQL. So let's take a quick step back and talk about some more general data modeling terms. So the first term that I want to cover here is called a RELVAR. That's otherwise known as a relational variable. So a RELVAR, think of that as a pointer to some structure that has a heading and will contain information. It is basically a pointer to something that we really want to call a table, but we shouldn't. So a relation is essentially a RELVAR at a specific point in time. So at this point in time, the relation employees is made up of a heading, which contains attributes and data types, and a body, which contains tuples. Second point of pronunciation, tuples instead of tuples. If you are a tuple person, that's okay. I'm going to call them tuples. Anyhow, the tuple people, go get your own talk. Go have your own talk on tuples. So we have in here a relation, which you think of that as essentially a snapshot at a point in time of a relvar. Then we have this concept of like what does a relvar actually mean? Can I put it into natural language? And the answer is yes, that's a predicate. So our predicate here is employee E works in the department D and earns a salary of S. And this is what the relvar is telling us. We can test propositions. A proposition is a statement that returns true or false. So this is how we understand if there is specific information that we can learn from a relvar. So we can learn that employee Marcy works in the sales department and earns a salary of $45,000 at time 1. And we can perform other propositions. Does employee John work in IT? And the answer is, according to the relvar T1, no. According to relvar at time T2, also no. So we can say, no, John does not work in IT based on the information that we have available here. The goal of normalization is removing redundant data is one of the goals, but fixing incorrect designs is at least as important of a goal. There are many ways that you can structure these relvars. Many of those ways are wrong, but it's not enough just to say, nope, that doesn't seem right. We want to have some sort of structured rules around when do things actually fit? How do things work and why do they work the way that they do? While at the same time, aiming for a design which is a good representation of the real world. It will be a simplification of the real world. All models are simplifications, but at least it follows what happens. So what I mean by that is, if I put together a beautiful logical data model for sales, and I hand it to the sales team to review, and they say, this looks nothing like our processes, it may be internally consistent with no redundancies and a technically correct design, but it doesn't fit what they do, so it's not proper, it's not correct. And also, we use normalization to simplify the statement and enforcement of integrity constraints. Define data model. A data model is a collection of relvars that serve to solve some business or some implementation purpose. Normally I would say business purpose, but yeah, it's a collection of relvars that are connected in some fashion because they help explain something that's of interest. That is my very off-the-cuff and probably poor description of a data model, but that's what I'm going for here. So rare to start from scratch. You always inherit these things. Yeah, it's true, Mike. It is rare to start things from scratch, and we'll keep that in mind as I go through some of the advice. Understanding that nothing will be perfect. There will always be opportunity costs. There will always be costs to make changes. So tonight's talk, we have a lot of normal forms to discuss. And like I mentioned, some of these kind of live in the academic world, as in Probably about a third of them I had never heard of until I started diving into this talk. And I'm still not sure that I could describe the difference between essential tuple normal form, redundancy-free normal form, and super key normal form, because they don't matter. All right. In an academic sense, they matter. For researchers, they matter. There may be a table in your environment that technically doesn't fit fifth normal form, but could fit super key normal form. So there's a possibility that it technically could matter for you. Likelihood of this happening is pretty low. We're going to focus on 5 normal forms tonight, and I've got them highlighted here. He is missing Anders' normal form. That's probably at the very top of the pyramid, Anders. This is the best normal form. So it's an exercise left for the reader. Now, because I enjoy ranking things, kind of what I do, let's talk about them in terms of importance. There are 2 most important normal forms. What is the final form? I think technically at this point it's like Super Saiyan, God Super Saiyan or something. But who knows? So, normal forms ranked by importance. The most important normal forms are Boyce-Codd Normal Form and fifth normal form. Boyce-Codd is so important it doesn't even have a number. Next, we have one normal form which is pretty important sometimes, and that's sixth normal form. After that, we have 2 normal forms that I consider to be overrated. First and fourth. Right, first normal form is overrated. I will briefly touch on that, but not too far because it's overrated. Rarely relevant. I don't want to throw these out and say, don't care about these at all, but it's not common that those come up, at least in the business world. Never relevant, second and third normal form. Don't take away their numbers. Just, you go first Boyce-Codd, fourth. Actually, first Boyce-Codd, fifth. Forget fourth. So, let's talk about that. Let's talk about it from first normal form. Mala says, I can see bodies of developers passed out all around if I dare even say there are 6 levels of normal form. All you got to do is say, we got to get all of these normal forms in place. I believe there's 11 there. You can do my math. Numbers have no meaning in terms of importance, like 6th normal form is not like an 8th degree black belt. So the numbers have a vague meaning. Essentially, the number is the order in which they were discovered. And they do happen to kind of go in terms of this is stricter than this is stricter than this. Doesn't each build upon the previous? Kind of. So the thing is that you had first, second, and third normal form, but second and third normal form were a diversion. They were a trap. The real normal form is Boyce-Codd. Boyce-Codd is the generic form of second and third. It's superior in every way. From Boyce-Codd, you can get to fifth. Fourth normal form is related to fifth. Sixth normal form comes outside of fifth, and then you've got other normal forms that kind of have some relevance. We'll talk about them as we go on, but I do want to jump to first normal form. First normal form, key rules and the shapes of tuples. So suppose you have some relvar, and it has a heading. That heading contains attributes. Each attribute has a data type. First normal form says all tuples in that relvar will follow the heading, which means that they will have the same attributes, they will have the same data types as what the relvar demands, and there will be one value of that type in that attribute. What the heck does that mean? When cleaning and analyzing raw data, first, second, and third normal form matter. I will say no, third normal form, second normal form don't matter. Let's talk Boyce-Codd in just a little bit. That's the one that matters. Now, I think I have to switch over to no cam so that you can read all the words, and then I'll be back. So in other words, we have a rel var. Let's call it user. And we have a relation. This is our snapshot of user as of a certain point in time. Inside user, we've got 3 attributes in the header. Username, which has a data type of char. Password, which has a data type of binary. Is active, data type of bit. Each tuple, therefore, must have the same combination of attributes and data types. If you add a new tuple, it must have the same attributes and data types. This is first normal form. So, 3 rules on first normal form. New tuples need to match the existing header. All tuples must have values for all attributes. Null actually violates first normal form. It's interesting to see CJ Date constantly ragging on null, that null is a stupid idea and it's a terrible thing. In the relational world, you go to the academic world, null is a travesty. So first normal form technically means cannot have null. Does the term null, does the phrase null violate first normal form? No, the string null does not violate first normal form. The concept of unknown violates first normal form, because what is the value of unknown? I don't know what its value is. That's why it's unknown. So the term value in there is specific, and it actually means a value, not either a value or some unknown which may represent a value later. No duplicate tuples. Attribute order does not matter for tuples, and tuple order does not matter for relations. So in other words, you can have the relation and the tuples can be in any order you want, and within a relation, the attributes can actually be in any order that you want. Joe Selko talking nulls. He used to be fiery. I'm sure he hated null. Seems to have gotten less intense about it. Yeah. I think it was interesting seeing that, again, the design people, and I would consider Selko in the design people world, they despise that concept and think that it's just an awful idea that opens up it's a Pandora's box. Finally, all attributes are regular. What does regular mean? It means they're normal. But not normal as in normalizing. They're just regular. They've got a name. They've got a type. They're not hidden. There's nothing special. There's no special weird metadata about them. So, for example, in Postgres and MySQL and Oracle, so definitely Postgres and Oracle, and I think MySQL, there is a hidden row ID, which is not available. Like you can query it, but you never create it in a table, and you never insert a value directly for it. So it's not a normal attribute. It's something that's kind of handled behind the scenes to make cursor operations faster. That technically violates first normal form because the attribute is not regular. Within SQL Server, identity values technically are still regular because they're still integers or big ints or whatever that you create. There happens to be a process that makes insertion easier, but you can still insert into them. You can still select from them, and a select star from a table still gets you those values. So it is essentially a normal column. Does anything like that exist in Teradata? Good question. The last time I've really used Teradata was probably about 15 years ago. So a lot has changed in the Teradata world since then. I don't think I could give you any answer at all on that, unfortunately. All right, Boyce-Codd Normal Form. This is where I have my throwdown and say second and third normal form don't matter because we got this thing. Boyce-Codd Normal Form, the most important normal form. It prevents a variety of data anomalies. So let's talk about some of them. Suppose we have some data. We have a rel var which is maybe a consulting company's information about the projects that I'm sending my people on. And this is the relation. This is a snapshot at a certain point in time. And we have specialists that we have working on projects, and we've defined specific tasks for them. Each specialist also has a login. Yeah, the term relvar is fun. I am probably going to accidentally say revlar several times as well. It is relvar, relational variable. So I'm actively trying to say it correctly. But now that I've said it the wrong way, I will say it the wrong way at least twice more. Guarantee you. All right, talk update anomalies. So here we go. I'll move over here. So Lindsay gets married. She changes her last name. We fixed it in the Spark project, but we forgot to fix it in the ETL project. That is an update anomaly. Next, we have redundant data. So we decided that, you know what, Julia and Lindsay, let's take you off of the ETL project, and our closer, Anne, is going to come in, lock this down. She's going to finish things up. So we're going to update each tuple and note that Anne is now working on ETL. But now we have duplication, no duplicate tuples. Got a problem. By the way, where was Anne? I just brought her into this, and you folks didn't know about her existence before then. So how do we make her visible when she's on the bench, not working on a specific project? I mean, I could have her working on like a placeholder, but that's not a real task, and it's not a real project. So that's a dumb solution. And all three of these are common problems that happen, and Boyce-Codd Normal Form fixes these sorts of issues. So we can define Boyce-Codd Normal Form as all functional dependencies have super key determinants. Now that that's clear, let's move on to the next normal form. So let's take this piece by piece. We're gonna go word by word, and the first word I want to talk about is super key. So a super key is a unique combination of attributes, but it is not necessarily the most parsimonious combination. So let us suppose that at our company, we have first name, last name must be unique, that combination. If you have two John Smiths, that second John Smith, sorry, we cannot hire you. We already have a John Smith. Go away. So first name, last name is unique. First name is a subkey. It is not sufficient to define an individual, but it is part of the answer. First name, last name, and height is a superkey. And a superkey is, yeah, you have a unique value, a unique tuple defined by this combination, but frankly, you didn't need height. You could have thrown that away and still had a unique tuple. So that's the concept of a superkey. Next, let's talk functional dependencies. Suppose that I have some attribute Z. Oh, any difference between a composite key and a superkey? So yeah, if I go back to this, a key can be one or more attributes, whatever makes things unique. So a composite key merely says, in order to become unique, I need more than one attribute. A superkey is, I have added attributes that actually don't make things more unique because it was already unique. So a composite key is just a way of saying you have multiple attributes. It's orthogonal. It's different from the concept of a super key or a subkey. So we have attributes X, Y, and Z. And the value of Z depends on the inputs of X and Y. So whenever X is 1 and Y is 4, Z is 7. And we can see that here, we can see that there. But I want to point out, the value of Z depends on X and Y, but not vice versa. So just because Z is 7 doesn't mean X is 1, Y is 4. So think of it this way. We're going back to high school or middle school pre-algebra. And I'm giving you a function. So what does a function say? A function says, for each element in the domain, there is one and only one element in the range. So for example, that is an example of a function. And you might say, well, how does this apply? Well, we can say, all right, well, that represents z, that represents x and y. And as we said, when x and y are some value, we have a value of z. If I drew this curve like that, this is not a function because for some combination of x, y, I now have two values of z. That is not a function anymore. All right, so functional dependencies, we got that math term in there. Basically, revising that, we see 1 for x, we see 4 for y, we know 7 is a z. And if I see that for all of the attributes, then I can tell x and y determine z. Or you want to rephrase that, x comma y is the determinant for z. So in mathematical terms, we write this as x comma y arrow z. Figuring out what these things are in practice can be difficult. So following the rules of math functions, it needs to pass the line test. Yes, it must be able to also recite the alphabet backwards and stand on one foot without falling over. So yeah, your functions cannot be drunk. Like I said, in practice, this can actually be really difficult. This is where ivory tower normalization and business world have some difficulty, because as a practitioner, you might say, how do I know what the functional dependencies are? And in the academic world, it's, well, suppose you have these functional dependencies. Great, how did you get there? There are a few ways to get there. One of them, so you have a couple of what I'll call deductive techniques and a couple of inductive techniques. As far as deductive techniques go, you can observe, hey, these attributes all have the same prefix, like customer name, customer address, customer join date. Those are probably all related to customers, and there's probably some key for a customer, some determinant, something that says when you see this customer X, this customer attribute, you will therefore see this customer name. You will see this customer address. You'll see this customer join date. So if we figure out what that thing is, we have a functional dependency. You can also talk to business people, try to understand the relationships between things. Even if they have wildly different names, it may turn out that, oh, a policy is functionally dependent, like a policy number is functionally dependent on these things. And if you understand those inputs that generate the policy number, then you'll be able to link them together. But that can be tough. It's going to involve some nice questioning of people and trying to understand if what they're saying is actually correct. On the inductive technique side, you may look at the data. I can observe this and see what is the cardinality of attribute X? What is the cardinality of attribute Y? If they match, can I see if they're, can I get the distinct set of the two and see if the number is the same? Can I look at multi-part combinations? Maybe I have correlation matrix to try to align how these things fit together. It can be tough. And so I don't want to minimize that. But I do want to say, once you have them, what you have is a definition. Because all functional dependencies have super key determinants. So a super key, we know, is a key plus maybe some more stuff. A functional dependency is a relationship between attributes that applies like a function. A determinant is the input for the functional dependency. So all relationships between attributes must have the inputs be a super key. It doesn't have to be a key itself, but it must be at least a key. And if you can follow that, your relvars in Boyce-Codd Normal Form are guaranteed to suffer from none of the anomalies we talked about. So how do we get there? Well, let me give you an example. So here I have a digital marketing campaign. We are going to start with a relvar whose heading has all of the attributes. I also like to call this a megatable because that's what the professor whose video I watched to learn this technique from originally called it. It's Jennifer Weedham. She is a professor, I believe, up in the Toronto area, and she called them megatables. I like the term. I pronounce tuples as tribbles. You know what, Solomon? I'll let that slide. So we start with a relvar whose heading has all of the attributes, everything we want to know about a digital marketing campaign. And we figure out the functional dependencies. We talk to the business people. We try to understand the processes. We may look at existing data if there is any. And we've come up with these 4 functional dependencies that a campaign ID functionally determines. I gotta draw my arrow like that. Functionally determines campaign name, campaign owner name, agency ID, maximum budget, and minimum bid. Agency ID by itself functionally determines agency name and take rate. So in other words, you don't necessarily talk to the business person and say, "Excuse me, Mr. or Mrs. Business Person, can you tell me all of the functional dependencies for the relvar in question?" Because you'll get even weirder looks than you're giving me right now. Instead, it's having a conversation. Okay, so what is a campaign? Oh, well, this campaign is it's an advertising campaign. We're launching it specifically to serve a set of products, and each campaign is going to be owned by some person at an agency. Okay, well, what is this agency? Oh, well, the agency is the organization that's managing all these campaigns. Okay, this take rate thing, that's the agency's percentage. Every purchase, they get this percent of the purchase. And so on like that, where you're sussing out these relationships. And by the way, what you're doing today is probably very similar in practice to what I'm talking about at the theoretical level. What you're probably doing in today is, hey, let's talk to the business person and we have a campaign. Okay, well, all right, let's talk about maybe a campaign table. And what is on a campaign? Well, we've got these things. Oh, you've got a list of these things. Maybe we should have that be somewhere else. So I'm not telling you what you're doing today is radically different. One of the interesting bits is a lot of normalization. Once you take the fancy math and formal logic out of it, a lot of it is common sense. And that's the plus side. There are bits that are difficult to figure out. There are bits that are not intuitive common sense. And we'll talk about some of those. But we've got these functional dependencies. Step 2, ask the question, are all determinants candidate keys? If the answer is no, then we have a problem. And in our case, the answer is definitely no. We know that the candidate key, I didn't tell you, but the candidate key here is campaign ID, audience target ID. So that is the candidate key of our mega table. That is the thing that makes our mega table unique. Well, we only have one determinant that is a super key of our relvar. So we got a problem. When we have a problem, we need a solution. And here's our solution, Heath's theorem. So Heath's theorem states that if you have some relvar and it's got components X, Y, and Z, as well as a functional dependency from x to y, we can break the relvar into two. One relvar contains xy, the other contains xz, and we can do this guaranteed without loss. What loss here means is I never lose a record in doing this, and if I combine these two back together, I don't have any phantom rows that appear. So this is otherwise called a lossless decomposition. That's really good for us. And by the way, x, y, and z don't have to be a single attribute. X might be the combination of campaign ID and audience target ID. Y could be some other attributes. Z could be 15 other attributes. So take this as a higher level, more generic concept that I can crack an existing relvar, splitting it by keeping the determinant in both relvars, and then splitting crosswise the other attributes out. So step 3 of our solution. If step 2 is no, we are going to, like prison rules, we're going to find the maddest, biggest, meanest inmate, and we're going to shank him. So we've picked agency. And what we did was we split out DM campaign into two relvars, agency and DM campaign. By splitting it out, we took out agency name and take rate. That was our Y. Our X was agency ID, so that stays in both sides. Our Z is everything else in DM campaign. Aggressive tech talks. I'm setting you up. These are important life skills. Critical life skills. So we now have an agency relvar. We have a DM campaign relvar. We repeat step 2. It says, nope, we still aren't done. So we do it again with campaign and break out campaign. As long as we have functional dependencies, which are not candidate keys, we just keep doing this process. So we do it again with audience target ID, because that is a subkey, not a superkey. And once I break out audience target ID, I finally have this structure. This is my final data model in Boyce-Codd Normal Form. And I also took the opportunity at this point to say, DM campaign doesn't make sense. Campaign target makes sense for a name, because I realize now that this isn't a campaign, this isn't a mega table, this is a very structured junction table between campaign and audience target. There I went slipping back into table talk. No from and through dates. When does slowly changing dimensions come into play? Keep that in mind. Keep that in mind. We will get to that, just not quite yet. We're not quite there yet. So here is Boyce-Codd Normal Form. And like I keep hammering at, Boyce-Codd Normal Form is the general form of second and third. The definitions of second and third normal form are specific to having a single candidate key. Boyce-Codd Normal Form says you can have as many candidate keys as you want, as long as each functional dependency's determinant is a superkey, then you are in Boyce-Codd Normal Form. And that also handles second and third, which is why I'm so willing to toss second and third normal forms under the bus, because we don't really need them at all. So let's now talk about fifth normal form. Fifth normal form is our second most important normal form. So what Boyce-Codd Normal Form does to functional dependencies, fifth normal form does to join dependencies. And our technical definition, a relvar is in fifth normal form if and only if every join dependency is implied in the keys of that relvar. So you ask, okay, where are you going with this now? So a join dependency. Suppose you have subsets of relvar R that are subsets of the heading, a join dependency holds if and only if that relvar can be decomposed without loss into its projections. So what the heck am I talking about here? What I'm talking about here is think of it in SQL terms. I have a table. I have a table with 6 attributes. If I can break this out into at least 2 tables without loss, then I should break it out into those tables without loss. So assuming that there is a join dependency, we're going to crack it out into 2 tables, like what we saw with Boyce-Codd. So I didn't want to go up there. Let's talk about a quick example. We have a supplier's relvar. It's got 2 functional dependencies. So we have supplier ID, which functionally determines supplier name and city. And we have a city functional dependency. So city functionally determines status. So in other words, I have suppliers who are based out of different cities. And those cities have a status, maybe some quality measure. So I may prefer Lafayette to Chicago and Lexington. Perhaps it's closer to my location and I can get goods out faster. So think of it that way. All right. So I have this relvar that's got supplier ID, supplier name, city, and status. A join dependency says that I can break this out into 2 components and reconstitute it without loss. I know this because Boyce-Codd Normal Form tells me split this out into 2. I have a functional dependency whose determinant is not a super key, because this is my candidate key. I might have an alternate key here, but this is definitely my candidate key. So city is not part of my key, and as a result, I need to split this functional dependency out into its own separate relvar. We learned that just a couple minutes ago. So in other words, there is a join dependency where I can say there's a join dependency with supplier ID, supplier name, city, and then a city and status. So if I can comfortably break these out and join them back together without losing any information, I should do it. That's what fifth normal form tells me. In other words here, functional dependencies are join dependencies. So anytime you have a functional dependency, you necessarily have a join dependency. But that doesn't work vice versa. So there are cases where you have join dependencies which are not functional dependencies. Before I get into one of those cases, let's circle back to Boyce-Codd Normal Form and say a relvar is in fifth normal form if, but not if and only if. So if it is in Boyce-Codd Normal Form and there are no composite keys, if all of my relvar's keys are single attribute, like supplier ID, supplier name, then assuming I'm in Boyce-Codd Normal Form, I am necessarily in fifth normal form. Already done. Problem solved. But as soon as you introduce composite keys, things get wonky. That's where we get to the connection trap. So suppose that we have some rules. If an agent sells a product and an agent represents a company and a company offers a product, then that agent must sell that product for that company. If this is true, we have what is called a symmetric constraint. If a symmetric constraint applies, we have a certain set of rules. If it does not apply, we fall into what is called the connection trap. So suppose all 3 attributes are here. And my specific example is people who are selling for an automotive company and they're selling specific types of or classes of automobile. So If all three attributes are necessary to determine which combinations are valid and which are not, we are in fifth normal form. In other words, Smith sells cars for Ford and Smith sells trucks for GM. If Smith is not obligated to sell Ford trucks, then we need to know all three of these pieces of information in one relvar. But let's suppose we have a different arrangement. So suppose we have agents Smith and Jones who are selling various products for Ford and GM. Ford manufactures both cars and trucks. GM only manufactures cars. And if we have that rule in place that says if Smith sells for Ford and Smith sells cars and Ford sells cars, then Smith sells for cars for Ford, we have a join dependency of three parts, where I have agent and company, I have company and product, I have agent and product. And if I have this join dependency, we can see that this join dependency is, none of these are keys. The key to my relvar here is agent, company, product. But I have join dependencies that are not the combination of agent, company, product. They are sub-keys of that. So we have a problem. And the answer is break it out. So now we have a situation like this, where we have agent, company, agent, product, company, product. Each is its own relvar. Each has its own key. And as long as our symmetric constraint holds, everything is dandy. But suppose GM starts selling trucks. What happens? Well, we've added a new row. We've added a new tuple to this relvar of company product. What logically must happen? And the answer is that because we have this GM truck, Smith must begin to sell GM trucks. Because Smith sells for GM, Smith sells trucks, GM sells trucks. So congratulations, you're selling trucks for GMC now. But suppose there is no such symmetric constraint, and we start with some similar data. But in this case, I wanted to clarify, and now Jones is selling GM trucks. Smith clearly does not sell GM trucks. Higher margins. Oh yeah, the pickup trucks are ridiculously expensive. I like short, fast cars, and you think some of those get expensive. High quality pickups, it's ridiculous. I can buy several of my car for a normal like 250 F250. Anyhow, that's a story for a different day. So we have Smith selling Ford cars, Ford trucks, GM cars. We have Jones who sells GM trucks. Clearly, Smith does not sell GM trucks. Just make that clear. Keep that in your mind. Suppose we look at that structure and we say, I can break this out into three relvars. I've broken it out. Is it correct? Well, when we combine things back together, we note that Smith sells for GM, Smith sells trucks, GM sells trucks, and therefore, if you were to take these three tables in SQL and join them together, you would get back a row that says Smith sells trucks for GM. And that is not correct. Not true. Fifth normal form seems a lot like overkill. Join dependencies are even tougher to understand than functional dependencies. I can't, if you held a gun to me and said, define a join dependency right now, I'm not sure I would do a great job. I would stammer and give you examples and kind of approach it. And here's the bad part. You go on the internet, people aren't better at it either. A lot of times you'll hear the term join dependency as the outcome of this problem, but this isn't a join dependency. The join dependency is the breakout of that relvar into sub-relvar, into like smaller relvars, in a way that is non-loss decomposable. That's a join dependency. Here's why it can be important. If you have no composite keys, Boyce-Codd Normal Form is fifth normal form. You're already good to go. We're solid here. If you do not have a relvar in fifth normal form, it can actually suffer from deletion and insertion anomalies. These are specific types of logical anomalies that are difficult to understand. So, as an example, suppose we have that symmetric constraint, but we kept 3 attributes in our single relvar. We didn't break it out into 3 separate relvars. In that event, we can have a problem where inserting one row logically necessitates that we add several other rows. So adding one tuple logically necessitates we must add other tuples because of this rule. So if, say, Toyota comes in and starts selling cars, and as soon as we say, oh, Smith sells Toyota, now we have to add in every single combination of Smith and Toyota and trucks and everything. And that may also necessitate that other people also change. Similarly, with deletion, by deleting one tuple, in order to be logically consistent, you may have to delete other tuples as well. In other words, these are complicated multi-tuple logic that is trickier to understand than the types of issues we see in Boyce-Codd Normal Form. And they're more difficult to diagnose. Also, symmetric constraints are actually not that common. But there is a common variation on fifth normal form that you'll run into quite a bit more often. You may never have a true symmetric constraint, but you will have the constraints that show up in fourth normal form. So I just called fourth normal form overrated like 6 hours ago when this session started. And yet now I'm coming to it and saying, it's kind of important. Here's what I'm talking about. Fourth normal form as a term is it's an anachronism. Fourth normal form is actually just a subset of fifth normal form. Relvar R is in fourth normal form if and only if every multi-valued dependency of R is implied in the keys of R. Back to the dictionary, what is a multi-valued dependency? Multi-valued dependency is a joined dependency with exactly 2 components. Why did they come up with the term multi-valued dependency? The reason is that the paper for fourth normal form was published a couple years before the papers on fifth normal form. Can I give an example? Yes, I will definitely give you an example, Mala. Don't worry. I'll give it to you in just a moment. So the papers came out earlier, the term came out, and as a result, we had fourth normal form, and then we had fifth normal form. And then later on, you realize that, oh, fourth is actually just a subcase of fifth. So what is a multi-valued dependency? Let's give you a scenario. We have courses. You have this course that can be taught by some teacher using some textbook. And each course, let's say it's a biology course, because I've got Dr. Skeleton in the back. So you have some number of teachers who are able to teach biology, and they can use some set of textbooks. And for that course, you have a tuple for every combination of teacher and textbook. So if I have 2 teachers and 2 textbooks, so teacher 1, teacher 2, textbook with an X, 1, textbook 2, I have 4 tuples. A multi-valued dependency here states that I can actually break this out safely into 2 relvars, one that contains course and teacher, one that contains course and textbook. I can decompose this and bring them back together and get back this exact relvar. It is non-loss decomposable. Another way that you'll see this written, because fourth normal form papers came out before fifth normal form, they had their own syntax. And so the top syntax with the asterisk is join dependency syntax. So asterisk here means join dependency. For a multi-valued dependency, you will see double arrow. So CNO, double arrow, TNO, and CNO, double arrow, XNO. Or you'll also see people write it as CNO, double arrow, TNO, type XNO. So formally, that's 3 different ways to write it, but logically, they're the same thing. And we get to Fagan's theorem. Fagan's theorem states that some relvar can be non-loss decomposed into XY and XZ if there is a multi-value dependency. Take Fagan's theorem, apply it to... There we go. Take Fagan's theorem, apply it to my relvar example above, and I can break that out C1T1, C1T2, and then C1X1, C1X2, 2 separate relvars. The relations each have 2 tuples, and it is recomposable. Is this the source of the original join syntax? Yes, and kind of. Join syntax is actually a little bit different. So Anders asks the question, what if T3 wants to use textbook X1 and textbook X3? Teachers can't use multiple textbooks. That's just a scientific fact. I mean, it's essentially in the rules that we generate. If you say that any teacher can use any arbitrary textbook and for teaching a course, then now this is no longer a multi-value dependency. Think of multi-value dependencies as independent attributes. So if you have attributes which are orthogonal to one another, split them out into multiple separate relvars. So let me give you an example of that. Suppose Mr. Smith quit his job as working at the car lot and is thinking about a new job. And he's thinking, I have 2 skills. I can cook and I can type. Furthermore, Mr. Smith, in addition to learning English, is fluent in German, French, and Greek. So how do we represent this information? And Anders says, so I've already broken the design based on changing business requirements. No, because that becomes a new design. You need a new design because you have new requirements. And so you design for the design that you need. That sounds very Herm Edwards-esque. You play to win the game. You play to win the game, Anders. What do these rules have to say about something like JSON data stored in a column? This goes back to first normal form, where in a lot of cases people will say having something like JSON in the database is a violation of first normal form. And Date's response is essentially not really. You know, as long as you have a value, that value can be whatever. That value could actually technically be another relvar. So you could have, thank goodness we don't have this, you could have a table as a value within a row, a table. And technically that's still first normal form viable. So essentially, the academic world makes the case that the data type itself doesn't matter as long as you're consistent and you have a value. You have a consistent value for that data type, for that attribute. And this is why you don't have academics design your database. I mean, you know, on the other side, Anders, if you don't have this rule in place, if you have all 3 attributes, Now you have a bunch of duplicate rows, or you have, excuse me, you don't have true duplicates. You have redundant information, and you run back into the issues of update anomalies. Date was a politician in some other life, considering his recent lines. That's possible. That's possible. So going back a little bit further to JSON, if you take it from the business world, or excuse me, from the academic world and try to apply a bit, and what you'll end up with is, my philosophy generally is, if I need to work with this thing within the database, I want a separate value. I want a value that represents the thing itself that I'm working with. So if I have a JSON that includes a customer ID, a customer name, and a customer address, if all my database is doing is storing this and then returning it back to some application that does work with it, yeah, that's fine. As soon as my application needs to search for customer names, now we got problems. Because now I'm digging into the value and doing things that probably shouldn't be done in that way in the database. So Anders says, I've had to take over a system designed by someone who wrote one of the books on relational database design. It was a nightmare. I could see that happening. Again, we are talking academic, and I will readily admit that applying the rules of academia to the world of business is not a one-to-one mapping. So, all right, back to fourth normal form. How do we represent this information? Well, for Anders' sake, we've come up with several designs. The first one I'm sure he'll like, which is disjoint format. You just have a new tuple for each skill and a new tuple for each language. But the problem is, what do these blanks actually mean? And what if Mr. Smith doesn't know any extra languages? At that point, do we have one row that just has blank? Or do we have no row? Or how does that work? So then we have the second design, minimal with nulls. But I read this and I say, well, this looks like Mr. Smith can cook French cuisine and type in German, but we don't know what he does in Greek. And by the way, what happens if Mr. Smith forgets German? So in that case, I now have to shuffle around. I can look at this and say, oh, clearly if he forgets German, I have to go to the row that doesn't have a skill, find that column that's Greek, and update the language for German to Greek, and then delete the row that has Greek. So that's only like a 4-step process. And by the way, that's with full knowledge of what to do. If you have no information, coming up with a generic answer for how you retain minimal with null is a pain. Minimal with repetition. So going even further. So Mr. Smith can cook French cuisine and type in German and type in Greek. So at least we learned what he can do in Greek. At least that's what it looks like. And again, similar questions. If Mr. Smith forgets German, then we delete a tuple. But if he forgets how to type, we now have to update 2 tuples. And if he forgets French, we can update 1 tuple and delete a tuple. Or we can update 1 tuple and update a second tuple. Or we have to do some combination of actions. So he can only cook in French. I mean, that's what it looks like when you read this, but technically we know it's that he can cook and that he can speak the French language. These are independent attributes. And if you combine these independent attributes together, we have troubles. This is unrestricted. This is all willy-nilly. And you never go all willy-nilly in your database. Point of life. I don't even know how to interpret this data. If you show me this, like this is your data set, I say, please clean up your data and come back later. Because we have all kinds of garbage in here. I think the design would benefit from XML. Where's that ban button? Mala, you've got ban rights. So here's a good solution. breaking it out into two relvars because this is a multi-value dependency. So, or in other words, it's a joint dependency of employee in skill and employee in language. And by separating them out, we no longer have any of the problems that we ran into before. ESL, technically, employee skill language was maybe good enough for Boyce-Codd Normal Form, assuming that the combination of the three was the candidate key. Now, arguably, bad solution number 3 can be in Boyce-Codd Normal Form, maybe. But 2 can't be because it has nulls. 1 can't be because it has nulls. And 4 can't be because it's garbage. So suppose we did option 3. It's technically good enough for Boyce-Codd Normal Form, maybe. But it's not good enough for us because that join dependency of employee skill and then of employee language really need to be broken out. By breaking it out, we get rid of these sorts of data issues, data quality issues. So, sixth normal form. Such a good normal form, I have trouble pronouncing it. Sixth normal form, if and only if all join dependencies which hold in R are trivial. Okay. What does that mean? Well, simplifying it, there may be one non-key attribute in addition to the key. All right. Actually, that's a pretty clear definition. Here's an example. We have a relvar of product, and it's got a product key and a product name and a color and a weight and a storage city. And our natural key is product key, so that is our candidate key. This relvar is in fifth normal form. And since we just talked about a case where we had 3 attributes and needed to break it out, let me explain a little bit why it's in fifth normal form. Product name, product color, product weight, and storage city are actually not independent. They are all dependent attributes on the product itself. And you may think about, well, skills are dependent on the employee, but it was really the combination of a skill and an employee. So your skills and your languages may both be parts of you, but they're not the same. They're not defining the same thing. The product name and the product color, this is the color of the product, the name of the product, the weight of the product, where the product is stored. So we're talking about a specific product here. And therefore, it's in Boyce-Codd Normal Form. It is a non-composite key. We're in fifth normal form. We can break this out into sixth normal form by giving each one of these non-key attributes in a separate relvar along with the key. Do we need sixth normal form? And Thinking Monkey says, maybe we do, but maybe we don't. And let's talk about why. If an attribute always has a value, it's probably better to cluster them together. Just keep them together because it's easier to work with that way. But if a value may be missing, you can break this out into sixth normal form to avoid null. We want to avoid null. And so let's say we might not always know what the product weight is, or it may not have a product weight. Perhaps there's some product which is ephemeral. It doesn't have a weight. And we don't want to put 0. So we could break this out into 2 relvars. One that has most of our product details, the other one that has product key and product weight. We can safely combine them back together, and we'll get back the same set of results. If we don't have a product weight for a product, we just don't have a tuple in that relvar. And therefore, when we join, we do want to have, in SQL terms, we would want to have an outer join to make sure that we still get back products without weights. So sixth normal form can help us avoid null. So that's kind of good. 6th normal form also works with intervals. So the Duke had a question about stored time and intervals. And this is where I want to talk about that. Usually, we're talking intervals of time, temporal data. Technically, it can be things other than time. You could actually have an interval of, say, currency, or an interval of heights. If it's a continuous variable, technically you can have intervals of it. But usually we care about this in terms of time. So suppose we have a supplier. I buy supplies from somebody, and my supplier is currently in London for days 4 through 8. I have a second supplier who's in Paris on day 3, and then in Athens between days 5 and 10. So I want to track where my suppliers are and track them over intervals of time and what city they're in. Do we need 6th normal form? Well, suppose we have a type 2 style slowly changing dimension, and interval is effective date and end date. Supplier 1 is in London with 4 assistants from days 1 through 8. Then supplier 1 picks up a 5th assistant on day 9, and from 9 to 14 has 5 assistants. Then supplier 1 takes all 5 assistants to Paris on days 15 to 17. Supplier 2 is in Athens with 3 assistants from day 1 to 17, and then hires a 4th assistant on day 18. So this table fits your classic type 2 slowly changing dimension. And it's a fine table. We can break it out. We can break it into 2 non-redundant relvars and say supplier 1 was in London from these days. Supplier 1 had 4 assistants on these days and 5 on these days. So now we have these 2 separate relvars that combined together tell us the same information. And to join them back together, we unpack the intervals. So day 1 to day 14 becomes 14 tuples. We connect together the elements based on that date, and then we repack the interval to get the minimum time frame. Essentially, I'm telling you, this is a gaps and islands problem. We have a tally table. We can split these out. We can figure out how things combine. We compress them back together, and we find the islands in which data fits. The islands in which supplier 1 was in London with 4 assistants. And that was days 1 through 8. So we can break out a type 2 slowly changing dimension into a set of independent intervals with with these types of relvars. Do we want to? Let's go back to the big cam and talk about that a little bit. And the answer, maybe. Let me tell you why it's maybe. If you have a system that is quickly changing, or you have several processes that can update your data, then a slowly changing dimension is not usually the best choice. If you a slowly changing dimension in that Kimball model really relies on having a single update process, and that single update process controls redundancy. So if you can't guarantee that single update process, then it does make more sense to break everything out into 6th normal form and to have your interval, your begin and end times, and your key and your single attribute, and then have perhaps a view that joins them back together so that it looks closer to what the slowly changing type 2 dimension may look like. If you're dealing with a warehouse where, again, you get to control that load process, you are the owner of it, in that case, this is overkill. You're not going to get much from here that you won't get elsewhere, except perhaps to be able to answer queries about single attributes better. So here I can answer the question of how many days, or on which days did supplier 1 have 5 assistants? And I can answer that very quickly, very easily. So if that's the sort of question that I'm frequently asking, this design might be better. But if the type of question that I'm asking doesn't really fit in those terms and fits more in classic, I need more information about a fact type of Kimball form, then that type 2 slowly changing dimension is probably going to be your better route. Managing a call center and queues. Yeah, possibly. How many people are working on which calls at what time? Basically, if you're working with things where you have time intervals, then 6 normal form can be interesting. If you're dealing with temporal data where you really need to know that history and you need to know changes over time, this is an efficient way of storing those changes over time. This may address storage issues as well to reduce storage for the Kimball form. Yeah, I kind of just gave that away. Yes, yeah, Raymond, it can. Though with the Kimball style, the concept is that the dimensions shouldn't be that large to begin with. So if you have dimensions that change really frequently, it's not a slowly changing dimension, and that's usually a code smell for a Kimball model. So is this more of an Inman approach? It's probably closer to that, but I wouldn't necessarily call it the Inman style either. My mind has that being a good bit different. But it's certainly closer in spirit than it is to a dimensional model. So speaking of which, let's talk about normalization and a couple of points. Like normalization and data warehousing, since I keep talking about it. Relational theorists, they tend not to like the Kimball model very much because the Kimball model is a business implementation. It is entirely intended to solve questions of how do I get a model that business people as opposed to technical people can understand and work with while still retaining enough of the benefits of a relational database system that everything doesn't fall apart. So as a general purpose relational model, the star schema is a terrible idea. It is prone to all kinds of anomalies, and it has an enormous amount of redundancy. But if you follow certain rules, the model can work out really well. That Kimball style can work, but you have to have one and only one process to write data. That is by far the most important rule. As soon as you have multiple processes updating data, they may have different business rules, different implementations, and now you have anomalies that can leak in. As long as you have one rule from one process, you can control and have a lot more redundancy safely. Your warehouse model, your Kimball model, has to be a proper model of business processes and understanding. So we talked about at the beginning, normalization. One of the goals is to have an appropriate design. And for the warehouse side, this has to be not just appropriate design, but also appropriate for the specific business processes. And then the fact dimensional concepts. So facts are measurements of things. Dimensions are information about things. And you use the appropriate slowly changing dimension type for each dimension. So the Duke says those bullet points feel like they're more in the spirit of Inman rather than Kimball. Yeah, this is definitely, I think it frankly is both of them. Except facts dimensions, those are definitely more in that Kimball approach. But the first two, one process to rule them all and a model based off of the business understanding over the technical design, yeah, they'll fly for both of those people. But Lord of the Rings model, yes, everybody eventually becomes Gollum. Well, I keep doing that. What I'm doing is I'm going to the next slide, except that's actually switching my view. So normalization, over-normalization. Over-normalization does not exist. If you use the term, it is safe to drop that term. You will lose nothing by it. So what people tend to see as over-normalization is usually one of two things. First, you're trying to remove legitimate business flexibility. Second, lossy decomposition and phantom rows. So let's talk about the first one first, because I put it first. This actually ties in with something Anders was poking at a little earlier, and that is there are cases where you may look at, for example, you have a list of products. So you have products, and you have orders and order lines. And on order line, you see, here's my product ID, here's my quantity, here's my price of the product, and here's my subtotal. You may look at that and say, now hang on a second. I have price of product, and I can see that on these products, this product has this price, this product has this price. That certainly looks like a functional dependency. And in fact, it's the product price. So I should put the price on the product table. And that might be correct. But let me lay out a scenario where perhaps a manager has the authority to change the price at sale time. And it's not just a discount. It's not a discount percentage. It's, I will remark this at this dollar amount per unit. If that's the case, then having the price on the product and having it on the order line can both make sense. One company I worked for, we did not know what was sold until the buyer reported what they had bought. Yep, I know what company Andrews is talking about. And that's a weird inventory situation. Essentially, your inventory is, we have a bunch of stuff. We don't even know how much we have or what they have or whatever. And we just need to know numbers so that we can do accounting. But if you're trying to remove that legitimate business flexibility, it leads to problems. What? Yeah, half-price books. So basically the idea is you get all of these books. People bring in books. They get priced out, like, okay, we'll pay you $4 for this book, and then they put it on the shelves. Well, a single store may have 10,000, 20,000, 30,000 books. Makes it great to walk into some of them sometimes. But they don't know what they have in inventory. It's not worth the money to try to keep track of all of those books and simply say, here is the shelf on gardening. If you want a gardening book, they're all labeled and priced, so bring it up and pay whatever amount the label says. And then at scan time, it's less of I'm scanning an ISBN and deducting that from inventory, and more of I just paid $8. Like somebody's paying me $8, and as a result, here's it was 2 books for $8. The Strand in New York. Yeah, that's another example of that sort of store. So in those cases, you may not necessarily have an inventory. If you walked into one and asked, do you have a copy of this book? They'll say, I don't know. Basically, it's probably over on that shelf if it's there, or it's in that section. But they're not necessarily going to know unless somebody actually stocked it. So it's a pretty cool use case where that upfront knowledge of inventory doesn't really matter for them. All right, that was legitimate business flexibility. There are cases where we may look at a rule and say, this should be a rule, but it really isn't. And if you try to apply that non-existent rule, that's not over-normalizing. That's just you're not doing the right design. You've gone into wrong design in an attempt to become more proper designed. Second, lossy decomposition, phantom rows. This was a case where we had the agents selling cars for a particular type of car for a particular company. If I try to break that out into 3 separate tables. And there is no symmetric constraint. When I try to bring that data back together, I get additional rows that should not have been there. If you get additional rows, that's not over normalizing. That's you've done something wrong. So it's not a normalization thing, it's an error. Normalization and denormalization. Classic knockdown, drag out fight. Let's talk normalization. Normalization has very specific rules. You can tell what form you're in and what you need to do to power up to the next level. With denormalization, though, you have no such rules. Because if you say, I need to denormalize this, all right, to what extent are you denormalizing it? What methods are you using to denormalize? How do I know that my data model is sufficiently denormalized or that I need to denormalize it further? And how do I know that it has been done correctly? Normalization is based on rules of math and formal logic. Denormalization is not. And as a result, I don't think it's possible to come up with meaningful answers to those questions except for I'll know it when I get there. And that's not very satisfying from a design perspective. So generally what happens with denormalization is I have attempted this design, this data model, and performance is poor. Therefore, I need to change performance. I need to improve performance. And that's a fair point. How do I change performance? Well, I've got a few options. And one of them is actually to denormalize, which could be introducing more redundancy so that I can collect information. Perhaps think of something as I mentioned the price and the quantity and the subtotal. Well, price times quantity equals subtotal. So somebody may denormalize by including subtotal so we don't have to do that calculation every time. That brings up to the question of, well, is that enough? Why did you choose to do that? Why did you not choose to do something else? And those are hard things to answer a priori. In an ideal world, we get back to that world of logical data model and physical data model. You have sort of the Plato and Aristotle type of image. And we've been talking up here in this Platonic logical model. Well, in an ideal world, we can talk about the Aristotelian physical model as being a separate thing which is conjoined and say, okay, the performance is poor because we need to do this operation. We need to join together these two tables. We need to perform these aggregations. We need to perform these filters, and those are expensive and takes a lot of time. So what if we could have a logical model that had everything broken out appropriately, but then was stored on disk, pre-aggregated, pre-filtered, pre-optimized? That's kind of the best of both worlds. And, in that scenario, we could have that physical model actually be a bit different from the logical model, but map to that physical model in a way that's understandable, where we still have rules to map it, but it would be quite different. And we have a very limited amount of that. Like I said, we've got indexes. We have say the possibility of storing data on multiple file groups and multiple files, so we can have it split across several disks. We can have memory optimized tables in SQL Server. We could have indexes, if I didn't already mention those. Materialized views, yep, we could have indexed views in SQL Server. So we've got a few options that are available. They're not necessarily great options. Like indexed views are cool until you hit the major pain points of indexed views, which is usually around frequently updating data and intense amounts of locking. But In that ideal world, we have the Platonic logical model, the Aristotelian physical model, and they're close but not the same. Denormalization is people's attempt to browbeat a Platonic model into an Aristotelian form. And that's what we end up with. So, given that, general philosophy on denormalization. Denormalization can be useful. It can be useful to increase redundancy when necessary. An example of that is data warehousing. We do a lot of denormalization to build out dimensions. But denormalization can add in invalid design ideas. That's the type of denormalization we want to avoid. We want to avoid that sort of denormalization where we had login, and when Julia changed her last name, we only changed some of the values for the login. So this is the risk that we run into. We reintroduce this concept of update anomalies. If we have a aggregation table, that aggregation table, you can make an argument about whether it's denormalizing, but let's just suppose for the sake of argument that that's denormalizing. There's debate. But I have an aggregation table and I have, say, a main table, and I roll it up. Every time there's a transaction in my main table, I roll it up into my aggregates. If somehow that process to roll up fails, I may not have these two in sync. And that is a design problem. It is an issue that is introduced by the fact that we're using this design. So we run into an inconsistency of answers. And if you have a database which is inconsistent in its answers, people stop trusting it really fast. If they say, this table tells me 12 and this table tells me 14, I don't know what the real number is, they stop believing either number. So that's the risk that we're trying to avoid. Finally, normalization and its discontents. So normalization is not all there is to relational design. Join dependencies, functional dependencies are important, but they're not the only types of constraints. And frankly, normalization doesn't help with other types of constraints. Multiple non-loss decompositions into fifth normal form are possible, but I don't know. If I have three possible options, I don't know which of the three to choose. So that's an example where I have this possibility, but I don't have good answers on how I get to which one. Which one is the correct one, because all three are logically consistent, but that's not a great answer that, well, all three are just equally fine. Applying academic advice to practical circumstances is not always a direct mapping. We talked about that a couple of times here. There can be difficulties in tying in even the stuff that I've talked about, functional dependencies, join dependencies. Understanding how those work in a real-life database can be a real pain. And finally, normalization is explicitly about the logical model, not the physical model. In that ideal world where we can modify the physical model much more significantly than the logical, we would have cases where my logical models and my physical models are quite a bit different. And one group of people lives in the logical world, one group of people lives in the physical world, and they can discuss between each other where changes come in. But in the real world, with SQL, logical and physical models blur together. And it's kind of a limitation of the relational database products that we have, and to an extent, even the language that we use. So, wrapping up, this has been a look at normalization from that academic perspective. I think this is a complicated topic, and hopefully I've straddled that line between being formally correct and being understandable. Hopefully I've helped you helped you understand a bit better Boyce-Codd normal form, fifth normal form, tying in sixth normal form. And if you'd like to learn more, you want to grab these slides as well as additional resources, csmore.info/on/dbdesign. And by the way, this is the first talk that I have come up with that has an explicit director's cut. So let me show that to you, because I came up with the original slides and I had so many additional slides that I wanted to include them. I included information on a previous talk I used to deliver that this is what I used to think about the world, and then this is how it changed. So I've got a director's cut version that I cut down for time so that we could finish at a reasonable hour. Whether or not this was reasonable, that's up to you. That's your call. So with that, everybody, thank you so much. If there are any additional questions, drop them in chat as I lose my voice from having spoken for the last 10 hours. All right, Mala says, I'm going to have to watch this a few more times. The VOD will be available, and I'm going to post that on YouTube pretty soon. But pretty soon, it'll be like one of these days. All right, if there are no other questions, everybody have a great evening. If you do come up with questions later on, again, hit me up. Let me try to get over here. So like Twitter, which I never check, and email, which I actually do sometimes check. Is my shirt ASCII art? So this shirt is actually, let me do this. This is Azure Functions. So yes, it is ASCII art. And with that, now that I've raised and lowered the table, everybody, have a great evening.